Let's say that a friend of mine and I have a bet going on. My friend believes that college students are no brighter than the general population. And for the general population, the mean is 100, and the standard deviation is 16. So that's my friend's claim. He says, college students just like everybody else. And let's say that my view is that college students are brighter than the average population. So, if you will, we have two hypotheses here. We have our research hypothesis and our null hypothesis. Null hypothesis is that IQ for college students is the same or even worse than the general population. Okay, so null hypothesis, college IQ is less than or equal to general IQ. Research hypothesis, what I'm hoping to show is that college IQ is greater than the general IQ. Alright, let's say it for sake of discussion where my friends agreed that I may randomly sample 16 college students who, if they are agreeable, will take an IQ test and we'll settle our bet based upon the average IQ of these 16 college students. Just how far above the mean of 100 do these 16 college students have to be before my friend should concede that he's lost the bet and he owes me the money? To do that, first we need to take a look at what would be the distribution of sample means if my friend is right and college students are no different than everybody else. So we know that for a population of individual scores, the mean is 100, standard deviation is 16. But what about when we deal with the distribution of sample means, where each sample mean represents 16 people? Here's that distribution of sample means. Notice it's narrow because each value is the average of 16 people, so we're not going to get very far away from that mean of 100. So mean of 100 for this distribution of sample means. But what is that standard error of the mean? Standard error of the mean is approximately equal to a standard deviation of the individual scores divided by a square root of our sample size. Our standard deviation is 16, so that is divided by a square root of our sample size, which is also 16. That ends out equaling 16 over, square root of 16 is 4, 16 over 4, which equals 4. So our standard error is going to be 4, and our mean is going to be 100. So it's a standard error of 4. One standard error above the mean would be 104. Two standard errors above the mean would be 108. One standard error below the mean is 96. Two standard errors below the mean is 92. Based upon the empirical rule, we know that 68% of those sample means will be within plus or minus 1 standard error, and that approximately 95% of the population will be within plus or minus 2 standard errors of the population mean. Well, that's all great to know, but really let's get back to this bet that's taking place. Just how intelligent does the average, how intelligent does my sample of 16 college students have to be before my friend should concede that he's lost the bet? That is, if let's say I say that they have to be 102. And I say, hey, is that going to be convincing? My friend's going to be like, nah, because if I'm right, 102 is not that uncommon. Well, I might say, what about 104? What if their average IQ is 104? You might say, well, that still could happen pretty often. I might go, well, what about 106? And you might say, well, we're closer to what I consider as reasonable. So I might say, well, what if we set it up so that the result would only occur due to chance, let's say 5% of the time. So in other words, we'll set some criterion so that the sample mean will only be that high 5% of the time if the null hypothesis is correct. On the other hand, if I'm right and college IQ is really better than general population, I expect it to be that high or above. That's called alpha. Alpha represents how often we're willing to mistakenly reject the null hypothesis. We're always going to have some alpha level. It's typically 5%.